Hi there, my name is Jorge Suarez. I'm in Professor Kim Chi's Physics 2 block, and the public lecture that I attended was The Hunt for Planet B on November 14th, 2022. The guest speaker basically gave a lowdown on transiting planets and the way that the new James Webb Space Telescope was finding planets that could possibly be habitable for as humanity may have caused Earth to be beyond repair, but that's another argument. Um, and it also went over a couple of other ideas such as variable stars, red dwarfs, and it also went over some of the physics principles that allowed the Webb Space Telescope to actually be able to take pictures of the galaxy so far. So yeah. So the first thing that I'm going to cover is the James Webb Space Telescope. So the James Webb Space Telescope was launched Christmas or December 25th of 2021. It's the newest space telescope to be launched, and it is NASA's biggest attempt to put something into space so far. It's actually weighs less than its predecessors as it's much better engineered. But something interesting about the James Webb Telescope is actually it revolves around the sun rather than the Earth. And this is a very interesting physics topic. It actually is at something called a Lagrange point, specifically L2 Earth Sun. So basically, the James Webb Space Telescope revolves around the Sun 1.8 million kilometers away, and it actually revolves around not necessarily perpendicular to the Earth, because this telescope actually moves around in a circle as it's revolving around the Sun. So it doesn't revolve around the Sun in a perfectly straight circle or elliptical line. It's actually moving around in a circle as it's moving around this larger circle. And that's due to the combined centripetal forces of the Sun as well as the Earth at the same time. So the centripetal force and the gravitational force of the Earth is actually pulling this towards it, causing it to revolve around in a circle, while the larger force and gravity of the Sun is actually causing it to move in the regular revolvatory shape that the solar system would be moving in. Something else that's pretty interesting about the James Webb Telescope is that it actually has so much heat insulation, and that's the majority of the actual body of the telescope, because on the hot side of the telescope, where all the computers and stuff, as well as the actual telescope, is on the other side, the sun side is at 185 degrees Fahrenheit and 85 degrees Celsius, and the other side is negative 388 degrees Fahrenheit and negative 233 degrees Celsius. So you could boil water and you could freeze nitrogen on the opposite sides of both sides of the telescope. The telescope takes these little bits of each piece of the galaxy and actually monitors them for 1 month, and it does this thing called the transiting method, which is the next part that I'm getting into. So the transiting method is basically this method used with the James Webb Space Telescope, where a transiting planet or exoplanet will cross in front of the sun and actually cause the brightness of the sun observed by the telescope to decrease for a slight moment. So if the telescope were to focus on one of the stars or multiple stars at one time, it could actually detect and create a curve of the light or brightness of the star that's in question. So these are light curves. They're based on brightness as the dependent variable and then time as the independent variable. And over time, you could see that as a transiting planet would cross over, there's this little box right here, which is categorical of exoplanets specifically, where the brightness decreases as the planet crosses in front of the sun in question. So the reason why this boxy shape or this rectangular shape is important is because there's certain things that'll cause a little bit of a change in the light curve that aren't necessarily exoplanets. An example of this is actually a binary sun solar system. So it's just like our solar system with a large sun in the center, but there's also a secondary sun that's revolving around the sun. The sun could have planets of its own and have its own solar system, but it's also a part of this larger solar system, and it'll have other planets revolving around the main sun in the middle. So the way that this changes the light curve is it causes this V-dip shape rather than the boxy shape that's categorical for an exoplanet. Another thing that can change a light curve is a variable star. So a variable star over time actually pulsates and changes size. So it'll start off small and then it'll actually increase in brightness as well as size, and then it'll shrink back down and be less bright. And this affects the light curve that is displayed by actually making a sinusoidal type of pattern where it goes up and down in brightness, kind of like a little weaving snake. So I found it pretty exciting, the way that we could actually find another planet for the future of humanity to dwell on, in case Earth goes bad for the rest of us, especially through just looking at stars and seeing what crosses in front of them, and having one of our new telescopes basically tell us where we could live in the future just based on how bright other things are in the galaxy. They also showed some really, really pretty pictures of the Milky Way galaxy in the public lecture that were pretty impressive. And then a couple of fun facts that I learned. I wasn't aware that cyanobacteria just figured out how to harness photosynthesis and created our atmosphere and gave it oxygen. That way, like, we could all evolve and actually start living on the surface of the Earth. So I found that pretty interesting. And then I also learned about red dwarf planets, which so red dwarf suns are actually suns that have began to burn out and get smaller, but they're much more dense than ours, and they radiate less heat and they're less luminous than our sun. So due to this, exoplanets that would revolve around red dwarf suns would actually be much closer to the surface of the red dwarf sun compared to us. So they showed a cool graphic that NASA created, and I recreated them on my own. And basically, it would look like this, where the red dwarf would be this close to the surface of the planet, and all of these foliage, as well as other living organisms, would have a red tint or red hue to them, and everything on the planet would be red and other corresponding colors. And not that that was pretty cool, because red's my favorite color. I just would like to live on a red planet. I think that'd be pretty cool.